Chapter 9, Day 2 of Section 1. So we are still taking a look at properties of radicals. There's a few more here that we got to discuss. First and foremost, let's talk about a radical in simplest form. Well, this is true when there are no radicals in the denominator of an expression. All right, now you can remove the radical from the denominator by this process called rationalizing the denominator. Essentially, what you're going to do is you are going to multiply the top and the bottom of that ratio by the radical expression that's found in the denominator. That will make sense here as we do our example. So let's take a look at example 1. We are going to simplify that expression. So you can see that we have the square root of 8 divided by the square root of 3. Well, this should tip us off. We can't have that radical in the denominator. So what we're going to do is we're going to multiply the top and the bottom of that that ratio by the radical expression that's in the denominator, which is the square root of 3. Now, when we multiply this, we're going to multiply straight across, numerator times numerator, denominator times denominator. And I'm going to end up with the square root of 24, that's my 8 times 3, in the numerator, divided by the square root of 9. All right, so something interesting happens here. The square root of 9 is a perfect square. And that should make sense because we are actually squaring 3, and that's the number under the radical. So when I take the square root of 3 squared, I'm going to end up with 3 in my denominator. So my denominator now is going to simplify to 3, and in my numerator I have the square root of 24. However, I shouldn't stop here. I can simplify the square root of 24 by breaking it down into two factors, one of which is a perfect square. So the square root of 4 times the square root of 6, and that's going to simplify to 2 root 6 divided by 3. And there is my final simplified solution. All right, let's try example B. We've got the square root of 7 divided by the square root of 2n. I'm going to multiply to get my square root of 2n out of that denominator. And the way I'm going to do that is I'm going to multiply both the top and the bottom by the square root of 2n. So when I square 2n, I'm going to end up with 4n squared. When I take the square root of that, my denominator will just be 2n. What I have in my numerator is the square root of 14n. And this is as far as I can go. I cannot simplify that any further. Don't be tempted to divide the 14 by 2. That 14 is underneath that radical, so you can't simplify that any further. All right, we're going to skip over example C, and let's move on with our notes. When an expression contains a binomial, remember that's two terms, with a radical in the denominator, you can rationalize that denominator by multiplying by the conjugate. Oops, I forgot a U in there, the conjugate. Now remember, the conjugate is, we've looked at conjugates before, and the way conjugates are formed, for example, here's an example of a root b plus cd. Its conjugate would be a root b minus cd. So the big difference here, to keep a note, conjugates just have these opposite signs. All right, simplify the expression by multiplying by the conjugate. So we have 7 divided by this binomial 2 minus root 5. So I'm going to multiply the top and bottom by the conjugate 2 plus root 5. I'm going to do the same thing here for my numerator, 2 plus root 5. So when I multiply 7 to that binomial, I got to distribute to both of those terms. So my numerator will be 14 plus 7 root 5. I can't combine those. I'm going to keep them separate. All divided by, I'm going to write out here, 2 minus root 5. There's one binomial, times the other binomial, which would be 2 plus root 5. All right, so when we multiply conjugates, we have to distribute, use that distributive property, or that foiling. So we're going to do 2 times 2, and that's going to give me 4. 2 times a positive 2 root 5, that's plus 2 root 5. a negative root 5 times that 2, so that's minus 2 root 5. And then I have a negative root 5 times a positive root 5. So that's negative square root 25. All right, now this is my entire denominator. Remember, my numerator up here is 14 plus 7 root 5. All right, so let's simplify. If you notice in the denominator, I have a positive 2 root 5 and a negative 2 root 5. Well, those are going to add to 0, and I'm left with just 4 minus the square root of 25, which is 5. So 4 minus 5 is equal to negative 1. So my final simplified solution here is 14 plus 7 root 5, all divided by negative 1. Now when we divide a binomial by a number, we divide both terms. So that's 14 divided by negative 1, and that's negative 14. And then that's 7 root 5 divided by negative 1, so that's negative 7 root 5. And there is our final simplification. All right, one more here. Let's do example 2b. We've got 4 that's being divided by the square root of 3 plus 1. I'm going to multiply it by the conjugate. So the top and bottom of this fraction need to be multiplied by the square root of 3 minus 1. And when I multiply my top, I'm going to distribute the 4. Oops, I accidentally wrote 4 in here. That should just be minus 1. Distribute my 4 in there, and that's going to result in 4 root 3 minus 4. Okay, in the denominator. And I'm going to do this in line here. Let's see if we can multiply this. We've got root 3 times root 3. That's the square root of 9. Root 3 times a negative 1. That's negative 1 root 3. Then I have a positive 1 times root 3, so that's plus 1 root 3. And then I have a plus 1 times a negative 1, so that's negative 1. All right, so once again, in your denominator, you've got these two middle terms here that add to 0. The square root of 9 is simply 3, and I have minus 1. So 3 minus 1 is equal to 2. And that's the number in my denominator. All right, so I'm going to rewrite this. I have 4 root 3 minus 4 all over 2. Now that means I need to divide both of these terms by 2. So 4 will divide into 2, or 2 will divide into 4 and leave me with 2 root 3. And then negative 4 will divide into 2 and leave me negative 2. So here we are. We've arrived at our final simplified solution of 2 root 3 minus 2. All right, flipping the page over, a concept that's not quite as difficult as the one on the previous page. We've got like radicals. Radicals with the same index number and the same radicand are called like radicals and can be combined in the same way that you would combine like terms. So here's a few examples. Simplify each expression by adding or subtracting radicals. I have 3 root 15 plus 2 root 13 minus 7 root 15. So as I look across, I see I have a couple of like radicals. I can combine those, and I have 3 plus a negative 7. That results in negative 4 root 15 plus 2 root 13. Now I can't combine these any further because root 15 and root 13 are not like radicals. All right, let's look at example 3b. I've got 5 root 7 plus the square root of 63. Well, it doesn't look like they're like radicals, but I can simplify the square root of 63 to be the square root of 9 times the square root of 7. Now I have 5 root 7 plus the square root of 9 times the square root of 7, and the square root of 9 is a perfect square. It's 3 root 7. So really what I have is 5 root 7 plus 3 root 7, and that results in 8 root 7. Well, I can do the same thing here for cubed terms or cube root terms. However, we're going to skip through the cube root terms this time, and we'll just focus on the squares and the square roots. Finally, I've got simplifying radical expressions by multiplying. Now, when I multiply radicals, I'm going to multiply the radicands. So here's what I mean. I've got the square root of 7 times the product, or sorry, the sum of root 3 plus the square root of 48. I know that I can simplify the square root of 48. So let's do that before we do our distribution. We've got the square root of 48 can be broken down into the square root of 16 times the square root of 3. Now, inside the parentheses, I've got root 3 plus the square root of 16 is 4 root 3. So really, these are like radicals, and I can add them together. I have 1 root 3 plus 4 more root 3, and then I have 7 times that, so that's 7 times 5 root 3. Now, when I multiply, I'm going to multiply the radicands underneath there, and that results in 5 root 21. All right, let's try one more example here. I've got root 2 minus the square root of 50, and then 8 root 3 plus the square root of 12. So these are products that I'm going to end up multiplying, but let's see if we can simplify first. I know I can break down the square root of 25, and this becomes root 25 times root 2. All right, and then 8 root 3, I can't break that down anymore, but the square root of 12 I can break down to the square root of 4 times the square root of 3. So simplifying one step further, I've got the root 2 minus 5 root 2, and then I have 8 root 3 plus 2 root 3. All right, so let's simplify some things here. I've got 1 root 2 minus 5 root 2, those are like radicals, and that's going to result in negative 4 root 2, and then I'm going to multiply that to 8 root 3 plus 2 root 3, and that gives me 10 root 3. All right, so following just multiplication, I've got negative 4 times 10, which is negative 40, and then root 2 times root 3 results in root 6. So notice how you multiply those numbers out in front, those coefficients on those radicands, and then you multiply the numbers underneath the radicands to get your final result. All right, try letter C here on your own and see if you can do a little simplification and then distributive property, and we'll discuss your answer in class tomorrow.